Before we begin with the first example, let's talk about for a second about the graphs of arcsine, arccosine, and arctangent. So if you remember from college algebra, to obtain the graph of an inverse function, all you have to do is take the graph of the original function and then draw the line y equals x, which is in this case is orange dotted line right here, and then you reflect across this line. So, for example, for the graph of arcsine, for sine inverse, remember that we restrict the graph of sine to the piece between negative pi over 2 and pi over 2. So in this case, it would be this one right here. Okay, so this would be the graph of sine between negative pi over 2 and pi over 2. What you do is you take that graph and then you reflect it across the line y equals x, and then that gives you the graph of sine inverse. So the graph of sine inverse would be this right here. I'm drawing in purple. Is a reflection across the line y equals x. Similarly, you can obtain the graph of cosine inverse. So the graph of cosine, in order to obtain the inverse, was the piece of the graph of cosine restricted between 0 and pi. So it is this one right here. Okay, and then you take that and then you reflect it across the line y equals x, which is the orange dotted line here, and you will get that. So the graph of cosine inverse is this piece. And similarly, you will do for the graph of tangent. Draw the line y equals x and reflect it across that line, and that reflection is the graph of the inverse function of tangent, so tangent inverse. Now, the graph of arcsine and the graph of arccosine are not really important. You don't really need to remember this. The things that I do want you to remember, though, are the domain and the range for sine inverse. That is important. The domain and the range of cosine inverse, that is important. And same for tangent inverse, but for the tangent inverse, you should really remember its graph as well. The graph of tangent inverse is more important to remember than the graph of these two. So the graph of tangent inverse is basically just a reflection of the graph of tangent. So it has the same shape, but it is between the horizontal asymptotes, negative pi over 2 and pi over 2. So that it has the same S shape. And it has horizontal asymptotes, negative pi over 2 and pi over 2. Okay, so these are the things, the ones that I have boxed up, the things that I want you to remember or memorize. All right, let's do the first example. It says, find the exact value of each of the following without the use of a calculator. So we want to learn how to do these without a calculator. First, because they're special angles, you should be able to write the answer down without using decimals. And second, because doing it without a calculator will help you understand what's going on better. All right, so let's do the first one. It says, figure out what is the cosine inverse of negative square root of 3 over 2. Okay, so we're looking for this. We don't know what it is. It's unknown for us. So let's give it a name. Let's give it a name and let's use the Greek letter theta instead of x because an inverse trig function actually spits out an angle. And remember that we normally use Greek letters for angles. So cosine inverse is going to spit out an angle. So let's use theta. Alpha, beta, all those are good. Okay, now after giving it a name, we're going to rewrite this equation without using inverses. Remember how that works. I want to write that using just regular cosine. And I can do that as long as I swap the input and the output. So writing this using regular cosine would be, well, the input now is going to become the output is going to become the input. So in other words, this is equivalent to cosine of theta is negative square root of 3 over 2. Okay, this is a negative number, and the ones we have actually only memorized are positive special angles. Angles in the first quadrant. So in the first quadrant, we're never going to get a negative. So think of then, for a second, think instead of what is the angle whose cosine is square root of 3 over 2. If we can think about this one first and figure this one out, then we should be able to figure this one out. All right, let's think about this one. So what is an angle whose cosine equals square root of 3 over 2? That is a special one, and you should be able to pull this from your memory. An angle whose cosine equals square root of 3 over 2 is actually pi over 6. Pi over 6 is the cosine of pi over 6 is square root of 3 over 2. The coordinates of that point are the cosine and the sine. The cosine is square root of 3 over 2. The sine, we don't need the sine, but just for review, the sine of pi over 6 is a half. Okay, so those would be the coordinates of that point. Now, what we're looking for is an angle whose cosine is not positive square root of 3 over 2, but it's negative square root of 3 over 2. So that means that x, we want the x coordinate, the first coordinate, to be negative. An angle whose first coordinate, cosine, is negative would be on the opposite side of the y-axis. So actually then, an angle that satisfies that property would be right here. A reflection, right on the other side. And that is the angle that we want. First, for two reasons. First, because indeed the cosine of that angle is negative, negative square root of 3 over 2. The coordinates of this point is negative square root of 3 over 2, a half. So it satisfies that. And second, because it is in the right quadrant, and this is very important. I'm looking for an angle that is spit out by cosine inverse. And there's actually infinitely many angles whose cosine equals negative square root of 3 over 2. And that's because cosine has period 2 pi. Remember, it repeats infinitely many oftentimes. It repeats over and over and over and over. Every time you add 2 pi, you get the same cosine. It has period 2 pi, so it repeats infinitely many times. So that means there's actually infinitely many angles whose cosine is negative square root of 3 over 2. But we don't want any angle whose cosine is square root of 3 over 2. We want the angle spit out by cosine inverse. And cosine inverse, which is the inverse of cosine, only will spit out an angle between 0 and pi. It will not be just any old angle. It has to be an angle between 0 and pi. So the angle that I want is between 0 and pi. So it has to be this one. You see what I'm saying? There's another one that has exactly the same cosine, that one. The coordinates of that one are negative square root of 3 over 2, negative a half. So the cosine is the same, but I don't want that. I want an angle between 0 and pi. So the answer is indeed this angle right here. That's my answer. So now, think about it. What is that angle? If this is pi over 6, what is that one? So if this is pi over 6, what is that one? If this is pi over 6, this one has to be also pi over 6 because it's a reflection. So I want almost all of it minus this piece. So it would be pi minus this piece, which is pi over 6. So the answer is 5 pi over 6. That's the angle that I want. The cosine of 5 pi over 6 is negative square root of 3 over 2, and it is in the right quadrant. It is in quadrant 2. It is between 0 and pi. So this angle checks all the two boxes. So that means the answer is theta is 5 pi over 6. Okay, part B. Let's figure out what is tangent inverse of 1. Okay, tangent inverse of 1 is our unknown, so let's give it a name. Let's say theta is tangent inverse of 1. Now we're going to rewrite that equation without the tangent inverse, the inverse function. So we're going to use regular tangent to rewrite the same relationship. Okay, if you want to, I want to use regular tangent. Remember how that's done. You have to swap the inputs and outputs. So the output is now the input, and the input is now the output. So in other words, tangent of theta equals 1. So we want to figure out what is an angle whose tangent of theta equals 1, and that's a special angle. You should be able to figure that out without a calculator because it's a special angle. It's positive, it is in the first quadrant. So think about it, what is it? The answer is pi over 4. The tangent of pi over 4 or 45 degrees is 1. Okay, so we found one angle whose tangent is 1, but before we declare this problem over, remember there's two boxes that we have to make sure we check. One is that the angle does satisfy the property of satisfying the equation. Two, the second box is the angle in the right place? Because it cannot just be any old angle. It has to be an angle, in this case, that is spit out by tangent inverse. Tangent inverse only spits out angles between negative pi over 2 and pi over 2. So you have to ask yourself, is the angle that I wrote down between negative pi over 2 and pi over 2? If it is, then okay, that's the correct answer. If it is not, then you have to change it. Find another one that is in the between negative pi over 2 and pi over 2 and satisfy the equation. This one works because pi over 4 is in the interval from negative pi over 2 to pi over 2. That's why this is the answer, because it checks both boxes. First box is the equation, second box is it's in the right place. So this is then the final answer. Okay, so this is really the general idea of how this is done. All of them are done the same way. So there's two more. Maybe you could pause the video and try these if you like, or just after I do C, pause the video and attempt D and see if you are following. All right, so let's do this one, C. Find the sine inverse of negative a half. Okay, that's our unknown. We're going to call it theta. So let theta be sine inverse of negative a half. Okay, now rewrite that without using inverse function. Rewrite that using the regular sign. So the output becomes the input, and the input becomes the output. Okay, so we want to figure out an angle whose sine is negative a half, first box. Second box, that angle has to be in the right place. And for sine inverse, the right place is between negative pi over 2 and pi over 2. Okay, I'm going to switch to another color because I'm going to consider a slightly different problem. To figure this one out, I'm going to ignore the sine for a second, and I'm going to try to think at least of an angle whose sine equals a half. Because I haven't memorized these ones, negative ones. I only memorize positive ones, the ones in the first quadrant. So I should be able to then think about what is the angle whose sine is a half. And pulling from your memory, you should know this. That angle is pi over 6. Again, all right. This is just coincidence. All right. So pi over 6. Sine of pi over 6 equals a half. We're looking, though, for an angle whose sine is negative a half. Negative a half, because we're talking about the sine. The sine is the y-coordinate. So we want an angle whose sine or whose y-coordinate is negative. So that would be this one right here. I want the y-coordinate to be negative. So this is the angle that I want. And that angle is negative pi over 6. So sine of negative pi over 6 is actually negative a half. So at least I found one angle whose sine is negative a half. So that's a potential answer. I don't know if it's the final answer until I check the second box. What is the second box? Is that angle in the right place, namely between negative pi over 2 and pi over 2? Is negative pi over 6 between negative pi over 2 and pi over 2? Yes. So that means it is the correct angle. So that means, going back here, that theta is negative pi over 6, pi over 6, because negative pi over 6 is in this interval between negative pi over 4 and pi over 4. That's why it checks both boxes. The sine equals negative a half, and it's in the correct interval. All right, let's attempt to the last one. Find an angle whose cosine inverse is negative square root of 2 over 2. Okay, that's our unknown. Let's give it a name. Let theta be equal to cosine inverse of negative square root of 2 over 2. Rewrite this with our inverse function. Just rewrite it using regular cosine. If you rewrite this using regular cosine, this becomes cosine of theta equals negative square root of 2 over 2. Output becomes input. Input becomes output. Okay, once more, I don't know off the top of my head, I don't know who's the angle whose cosine equals negative square root of 2 over 2 because I only memorized the positive ones. So let's draw a picture and see if we can figure this out. So if I just think for a second on an angle whose cosine equals square root of 2 over 2, ignoring the positive for a second, then I can answer the question because that's a special angle in the first quadrant. And that angle, what is it? You should know this. You should know this. This is pi over 4. Okay, it's a special angle pi over 4. All right, that's not what I want though, because I want it to be negative. Cosine is the x-coordinate. Cosine is the x-coordinate, so I want to be on the other side of the y-axis, so I want to be right here. This is then, I suspect, the angle that I want. That angle will satisfy the cosine being negative. And what is that angle right there? That angle is pi minus pi over 4, which is 3 pi over 4. In other words, the cosine of 3 pi over 4 is negative square root of 2 over 2. Cosine is the x-coordinate and it's on the left. It's negative. So that is the actual answer. Why? It checks both boxes. Let's talk about it. I say that the answer is 3 pi over 4. Why? It checks both boxes. First box is the cosine of that angle is what I want, negative square root of 2 over 2. That's the first box. Check. Second box, it is in the right place. What is the right place for cosine inverse? If an angle split up by cosine inverse. The right place is between 0 and pi. And 3 pi over 4 is between 0 and pi. Okay, there's other angles. Cosine is negative square root of 2 over 2. For example, this one right here. But that's not in the right place. The reason this is the final answer is because it checks both boxes.